Here are the caches practice problems. So the first question here was about drawing diagrams of caches. And we had three different types of caches to look at: a 64-line direct mapped right through with 8 bytes per line, 256-line fully associative right back, and a 4096-line four-way set associative. So let's take a look first at this one. So a direct map cache is going to have a tag and it's going to have data. And we have an 8-byte line. That means we're going to have 2 words per line, so 2 data words per line. And we also need to have a valid bit in here to know if this line of data is valid. And we've got 64 of these lines, so this is what our cache is going to look like. 64 lines with 2 words per line, a tag, and a valid bit. So then we need to have another cache here where we have 256 lines. So this is fully associative right back in 16 bytes per line. So 16 bytes per line means we're going to have several more of the words per line. So we have 4 words per line here. We still need a valid, and because it's right back, we need a dirty bit to know if the data is dirty. So we've got a dirty bit in there. Now I've got 256 of these, so we're going to have 256 lines. The last one has 4096 lines, four-way set associative, right back 64-byte lines. So we're going to have a whole bunch of these, 16 words per line, and a valid and a dirty bit, and then another 16, another, and another. And this is four-way set associative. So in each set, we're going to have 4 lines here, and then we're going to have 1024 sets. So it's 1024 sets times 4 ways per set gives us our 4096 lines total. Now we're going to figure out how the bits are used for addressing. So when we go to access these caches, we give it a 32-bit address from the CPU, and some of these bits are used for selecting the byte, the word, the index, and the tag. And let's figure this out. So here's our 64-line cache. So we have 8-byte lines, so we've got 2 words per line. To select one of those 2 words per line, we need 1 word bit. And we've got 64 lines, and this is direct mapped, so we need 6 bits to directly index into the direct map cache. So we have 2 bits for the byte. We're always going to have 2 bits for the byte because every word has 4 bytes in it. 1 bit to choose the word in the cache line because we have 2 words here. And then we have 6 index bits left, and those index bits tell us where we go in the cache because it's a 64-line direct map cache. So for the fully associative cache, we've got 16-byte lines. That's 4 words per line. We need 2 word bits to choose one of those 4 words. The 256 lines are fully associative. That means we don't have any data for the index because data can go anywhere. So here we have 2 bits to determine the byte and the word, which we always have, and then we have 2 word bits to determine which word because we have 4 words per line. For the 4096 line one, we have 16 bytes per line, so 16 words per line, so we need 4 word bits, and we've got 1024 sets, so we need 10 bits for indexing. Now remember, we have 4 ways in each set, so within each of those, choosing those 4 ways, we don't need any bits because they're associative, so it'll choose based on the tag. So this gives us 2 bits for the byte, 4 for the word, since we have 16 to choose from, and then we have 1024 sets, so we need 10 bits to choose one of those sets. Okay. So in the direct map, we choose the index directly, so we need a lot of index bits to choose exactly the index. In the fully associative one, lines can go anywhere, so we have no index bits. And in the set associative, we have some index bits, but not as many as we have lines, because 4 of those lines for every set are spent choosing where to go, or are chosen by the cache itself, so they can be anything. So how much overhead do we have for the caches? So for the 64-byte line, how much are we going to spend on data and overhead, and what's the percent of data? So here's the way we're going to index this. And so for the data, we have 64 lines. Each line has 8 bytes of data. Okay, because we have 8-byte lines. So that's 4096 bits of data. Now how much overhead do we have? So for each of our 64 lines, we have 23 bits of tag plus 1 valid bit. So that's 1536 bits. That's 73% data. Now we don't need to store the index bits or the word bits or the byte bits because the address tells us that. So if we're looking into the cache, we already know these bits in order to look there. We just need to know the tag bits to see what's there. How about this cache? So in this cache, we had a lot more tag bits because we didn't have any index. Data could go anywhere. So here we had 256 lines, but each line had 16 bytes of line. So we had 32,000 bits of data. The overhead was 28 bits per tag per line, plus 1 valid bit and 1 dirty bit, so 7,600 bits. So here we're 81% data. The larger cache here, we had 4,096 lines, each 64 bytes. So each line was 64 bytes. We had 4,096 lines. Remember, they were organized into 1024 sets of 4 lines each. We still had 4,096 lines. So that's a lot of bytes. It's 2 million bits here. Sorry, 2 million bits here. The overhead for each line, we had 16 bits of tag plus one valid and one dirty bit, so only 73,000 bits. So this is 97% data. So if you look at these, the reason we have so much higher percentage data here is because we have larger line sizes. We have more bytes per line, which means we have fewer tag bits for each data bit. So larger lines reduce the overhead. All right, now let's take a look at where the data goes. So here we have three different caches. We have a fully associative cache, a direct map cache, and a set associative cache. And we're going to look and see what happens when we go through this access pattern, 0, 1, 2, 3, 4, 0, 4, 0, 2. And the way I'm going to draw this, I'm going to have the least recently used thing on the top so we can keep track of what gets kicked out. But in the real cache, it doesn't move data around based on what's least recently used. So let's go ahead and get started. So in cycle 0, we access memory address 0, and we're going to miss in the fully associative cache because it wasn't there, and we can put the data anywhere in the cache. So we'll put it up here. For the direct map cache, we're also going to miss because the data wasn't in the cache, but we can only put it in one place, and that's this first entry because we address it as 0 mod 4, which gives us 0 and puts us in here. For the set associative cache, we're also going to miss because there's nothing in the cache, but now we can only put it in this set because this set is chosen by 0 mod 2 since there are two sets, which means all the even addresses are going to go in this set and the odd addresses in that set. We go to address memory address 1, we're also going to miss everywhere. In the fully associative one, we can put it anywhere. I'm going to draw it on the top here because it's the most recently used. In the direct map, we can only put it in one place. So address 1 can only map to here. And for the set associative, this is an odd address, so it's going to have to go in the odd set over here. For address 2, this is similar. Address 2 can only go one place in the direct map. In the set associative, it has to go into this set, but it can go in either of these places. And I'm going to draw it up here just to keep track of this being the most recently used one. For address 3, we're again going to miss. Address 3 can only go one place in the direct map cache, but it can go anywhere in the fully associative, and I've drawn it here as the most recently used. And for the set associative one, it has to go in the odd set over here, but it can go anywhere in that odd set, so I'm going to draw it at the top. Now our cache is full, now things get interesting. So we go to access memory address 4. Memory address 4 isn't in the cache, so we have to kick something out. So from the fully associative set, we're going to kick out the oldest thing here, which is 0. So now we don't have 0 in the cache. From the direct map cache, we don't have any choice. Address 4 only maps into this entry here, so we have to kick out what was there before, which was 0. For the set associative cache, it maps into this first set, so we kick out either of these two things. And if you look before, 0 was the older one, so we're going to kick out 0, so we have 4 and 2. So for the direct map cache, it doesn't matter that we're least recently used because each thing can only go in one place. Now we go and access memory address 0. Remember, we just kicked out memory address 0. So for the fully associative one, we're going to miss because we just kicked it out. And then we're going to kick out the oldest thing there, address 1, and put it in. For direct map, there's only one place address 0 can go, so we're going to kick out 4, which we just brought in and put in 0. And for set associative, we can put it anywhere in this set. We're going to kick out the oldest thing in the set, which was 2, and we're going to put it in here, so we have 0 and 4. Now we go and access memory address 0. Sorry, this is the same thing here as cycle 5, just bringing cycle 5 over here. Now we go and access memory address 4 again. So now we have a hit in the fully associative cache because 4 is in there, and 4 becomes the most recently used. We have a miss in the direct map one because remember we just kicked out 4 to put in 0. So now we kick out 0 and put in 4. And we have a hit in the set associative one because we had 4 in there before. Now we go and access memory address 0 again. Now we're going to hit in the fully associative because 0 is there. We're going to hit in the set associative because 0 is there. But we're going to miss again in the direct map one because the direct map one just kicked out 0 to put in 4 after having just kicked out 4 to put in 0. So you can see what's happening in the direct map cache here. 0 and 4 are conflicting because they can only go in one place, and we keep kicking them out. So we're missing every time, even though we have plenty of space in our cache for stuff we're not using. Whereas the set associative and the fully associative have more flexibility and can make this work better. So finally, we go and access memory address 2. We hit in the fully associative. We hit in the direct map because it was down here. It didn't get kicked out. But we're going to miss in the set associative. And we miss in the set associative because 0, 2, and 4 all map to this set, and we kicked out 2 when we were loading 0 and 4 into them. So why didn't this work? So when we have this address pattern 4040, the fully associative can have both 4 and 0, so any 4 lines. The direct map, 4 and 0 map to the same line. They conflict, so only one at a time. We kept kicking them out. And in the set associative, 4 and 0 map to the same set, but since we can have any 2 lines in the set, we could keep them both. Now when we went to access 2 later, we had no problem in the fully associative because it can have anything. It can have 4, 0, and 2, have any 4 lines. The direct map was okay. 4 and 0 mapped to the same line, so they were a problem, but 2 maps to a different line, so we didn't kick it out. For the set associative, however, 4, 0, and 2 all map to the even set. So that meant we could only have 2 of them in the cache at any given time. When we went through 4 and 0, we kicked out 2. So please keep in mind, caches don't actually move the data around. I just put them in that order in the picture so we could keep track of it. Now here's another question about average memory access time. So we have a hierarchy here with 2 caches, and we're going to go through it, and we have 65% of the benchmark's instructions are accessed from the L1 cache, and the rest come from the L2 cache. So what's the average access time for one instruction? And then we have a question, if we change the L1 around so that it has a higher hit rate, how's that going to change? Okay, so here we have 65% of the time we hit in our L1. If we look at our L1 here, it takes 1 cycle, plus the rest of the time, 35% of the time we hit in our L2, which is 5 cycles. So it's going to be 2.4 cycles average for one memory instruction. Now what happens if we change this? Well, if we change it, we now have 85% hitting 1 cycle. So this goes up to 85% 1 cycle and 15% for our 5 cycles. So it goes down to 1.6 cycles. So what's the speed up? Well, it's 33% faster. So if we can increase the effectiveness of our L1, that's great. How can we go even faster? So here we're going to change our cache line to be 4 words. Now each time we access the cache, we're going to get 4 instructions. Okay, so if on average we use 3 out of those 4 instructions, what does it do to the example before? So 85% of the time the cache line is in the L1, we know that from before, and each time we get 3 instructions in the cycle. 15% is in the L2, and each time we get 3 instructions in the cycle. So by making our cache line 4 words long and using 3 out of 4 of them all the time, we're getting 3 times as many instructions in the same amount of time. We've increased the amount of instructions we get from our cache by making it larger. So we effectively make it take much less time. So we're getting much higher throughput by having a larger cache line. And the reason this works is we have this locality. We were lucky that on average we use 3 out of 4 of the things that we load when we have a larger cache line.